First, let me say something about the homework assignment. Yeah. I just give you the part B of assignment number 3. We have one more left. Yeah. So after number 3, our last assignment, number 4. Yeah. So here, let me say, give you some updates about the plan of the remaining of the semester. Yeah. The deadline for part 3B, homework assignment 3B, this month, 20th, Sunday. Yeah. So you have plenty of time. Okay? Yeah, you have plenty of time. Yeah, but even that, you need to start working as early as possible. Yeah, because the previous 2 times, some students, couldn't complete it by the deadline. Yeah. So this time, because we are very close to the final, we won't have that much time. Yeah. So look at the remaining of the semester, the time we have left. So my homework assignment number 4, when I assign it, there is some overlap. That means before the deadline of assignment 3B, I need to start posting assignment number 4 to give you plenty of time. Okay? Yeah. So that's something you need to be, aware of. Yeah. So so first, for the assignment 3B, when you look at the question, I try to not make it too hard. Yeah. Because my original plan, I plan to give you 3 questions, power series questions about the Frobenius method. Yeah. We have case 1, case 2, case 3. Yeah. So each case, you need to do 1 example. But yesterday when I made the question, I realized, that's probably too much work for you. Yeah. Because the power series solution, you need to do a lot of calculation. Yeah. So considering, that I don't want to make it too hard, I only give you 1 question. That's the case 1 for Frobenius method. Yeah. That one, you can see I leave the whole page space. Even whole page space, it may not be enough for you because there are 2 solutions. 2 solutions, probably, some students use extra page to complete it. Because 1 page, you can only complete 1 solution, first solution. Then you have second solution. You need to, repeat the same thing. Yeah. Yeah. So for that reason, I only give you 1 question, 1 such question. Yeah. All right. So there are other questions. Yeah. So some questions not very hard, but you need to familiar with our materials. Yeah. You need to be able to at least find locations in our notes. Yeah. Some questions, if you are familiar with the materials, pretty easy. Yeah. Yeah. All right. Yeah. So that's the 3B. Then homework. The last one, I plan to do this way. Number 4. Still part A, part B. Yeah. I split part A, because in this way, I can give you a part A first, then part B. Yeah. Part A for me, I can give you, relatively earlier. Yeah. So part A, this time, I will give you 15 concept questions. Yeah. Actually, for each assignment, you can see we have 15 concept questions, right? But 10 computation questions. So part A, I just give you 15 concept questions all together at the same time. Okay? Yeah. Yeah. As a quiz, the format as a quiz, but I do not call it a quiz, okay? I call it the part A of homework assignment number 4. Yeah. But I do not call it a quiz, okay? Yeah. Notice this different. Yeah. The format So you know the format of the quiz. Format equals the quiz format. But I do not call it quiz because we only have one quiz left, right? After quiz 5, our last quiz, I want to use the last quiz for the final, okay? For the final part A. That's our quiz number 6. So I reserve it for the final. So I don't want to use it up, okay? Yeah, but here, yeah, because the quiz format very convenient, right? So for me, for you, all convenient. Yeah, but I just create a, I do not. It's not in our quiz list. It won't appear in our quiz list. Yeah, but format, yeah, quiz. All right. Yeah. So then part B, still 10 computation questions. Yeah, I mean, so I post last 10 questions, computation, okay, about the topic, all about Fourier analysis, okay, all about Fourier analysis. Yeah, yeah. The last quiz all about Fourier analysis. Yeah. Yeah. Okay. All right. Then the final exam. Yeah. Final exam. Yeah. Because final exam, in person, in class. Yeah. Yeah. 2 hours, right? Yeah, I will post the classroom. Yeah. I just received the classroom, not in this classroom. Yeah, I noticed that. I received the classroom information last week. Yeah, the same time, same day. Yeah, as in the syllabus, same day. May the 6th. Yeah, that's the same as our syllabus. May the 6th. Okay, Tuesday. Yeah, the class time. 2 hours. Yeah, yeah, but the building is not this one. Yeah, I couldn't remember the building. Yeah, yeah. So I will post. Yeah.
What if you won't be there?
I will. I will.
I won't be there.
Oh, you won't be there. You won't be where?
I won't be in Missouri on the 6th.
Oh, all right. Yeah. Yeah, all right. So there, but at the test time slot, will it be available? That same time slot. This time slot, will it be available? Can you do? You cannot. Oh, driving. Okay, all right. Then we find a different time. Okay. Yeah. So I will do the Zoom way. Yeah. We will do the remote way. Yeah. When you have a good, comfortable time slot, then you let me know. Yeah, so then we do a Zoom way, okay? Turn on your camera. Yeah, I can see you, So then, then you use the same 2 hours to complete. Yeah. All right. Yeah. Yeah. So I will let you know the classroom. Yeah. All right. Yeah, I don't know why they changed the classroom. Yeah. Anyway. Yeah. Yeah. Still part A, part B. Okay. All right. So final. Yeah. Part A. The same as the quiz, 6. Yeah. So I will post a little earlier. Yeah. A little earlier. Yeah. Than this time. Yeah. A few days earlier. Yeah. Probably the previous weekend, so about the Friday, Saturday before this date. Okay, I will post the quiz number 6. Yeah, but the same as the final. All right. Then part B. Still 10 computation questions. Yeah, 10 questions already quite a lot as for the 2 hour time, quite a lot. But some questions are relatively simple, right? Yeah, I mean, some questions, yeah, not very hard, Yeah. So because our quiz, our standard quiz format, 10 questions, right? Yeah, that's our standard quiz format, 10 questions. So I do not want to change. Okay, so in total you have 20 questions, not 25 questions. Yeah, shorter than our standard assignment. Our standard, we have 25 questions. All right, but I use the same way. Each question worth 4 points. Yeah. Each question worth 4 points. Okay, all right. Then, because we have 5 questions fewer, that those 5 questions equal to 20 points. That 20 points I give you free. Okay, you get 20 free points. Yeah, in this way, hopefully make sure you can get a decent grade. Yeah, in this way. Yeah. Another one, remember last time I mentioned you can list the 3 questions for the second chance. Remember? Yeah. I allow you, on your test paper you can list 3 questions you like to have second chance. After you get home, I will post your second chance questions. Yeah, but I will do statistics. I collect, all of you submit your list. Yeah. So I do statistics. Question 1, how many? Select question. Question 2, how many? All right. Yeah. Question 10. After I will start from the highest number first. But when I post, I will post the 5 questions, not 3 questions. Top 5 in the counting numbers, top 5. But you just select 3 from the 5. Okay? Yeah. You select 3 from the 5. So give you some room. Okay? Yeah. Second chance. Yeah. Because you may feel your 3 questions may not be in the list, right? Yeah. There is a chance your 3 may not be. Yeah. So I expand to 5 questions. Then more likely, so your selected questions, will be in the list. Yeah. Yeah. All right. Yeah. So that's the plan. Okay. Yeah. The remaining semester, the arrangement. Okay. All right. Yeah. All right. Let's start. Yeah. C.1, constant coefficient systems of ODEs. So let's solve. Yeah. This, linear system. So, yeah. Constant. But although the constant coefficients, yeah. Remember, we need to work on the non-homogeneous. Yeah. Homogeneous, very easy. But non-homogeneous, remember, there is a G part, G term. We need to, find a way to get a particular solution. Yeah. All right. Constant coefficients. Yeah. Homogeneous, yeah, but this time, yeah. Remember the example we used before, the 2 by 2, matrices, right? 2 by 2. Yeah. But we want to expand our theory to n by n, n-dimensional. N-dimensional, yeah? So we can easily extend it to n-dimensional case. Yeah. All right. The theory, pretty much the same. Yeah. The theory. Yeah. All right. Y prime equals AY. Yeah. You can see this notation, we can represent n by n. Yeah. All right. The coefficient matrix A is an n by n constant matrix. Yeah. Here, a constant. That means each entry constant. It's not a t function. Yeah. T function. It's possible each entry could be t function, right? Then it will be much harder. Yeah. T function. Think about that. If it's not constant, t function, much harder. Yeah. All right. Consider a solution with the form. Yeah. Now we try to understand the solution structure. Yeah. The solution, remember eigenvalue, eigenvector. Yeah. So we use the eigenvalue, eigenvector way. Y equals x vector times e function, e to the lambda t. Yeah. X, that's the eigenvector corresponding to the eigenvalue lambda. Yeah. That structure. Okay. The typical structures. So each solution function, we use this structure. All right. X constant vector. Yeah. Yeah. All right. So now here, yeah. So we just, we did this for 2 by 2. Yeah. Here, we repeat the same thing for n by n case. Yeah. Y prime, yeah. Y prime, X constant vector, so we keep it. Yeah. The E part, we apply the chain rule. Yeah, so lambda times this same vector, okay? Yeah. All right, y prime, yeah, because by the original equation, y prime equals A times y vector, A. Yeah, so here, this the second equality based on the original equation. Yeah. Then, all right, so we can, yeah, so here, you can see, with this equality, we can cancel out e function part because e function never be 0, right? E function never be 0. Yeah. But here you can see x vector we can now cancel out, right? Yeah. So vector multiplication, don't do cancellation, okay? And vector part. Yeah. All right. So we, after simplification, we have ax equals lambda x. This is the equation we use to find eigenvector, right? Yeah. So if we have the eigenvalue, how to find the eigenvector? This is the equation we use to find the eigenvector. Yeah. All right. All right, so it's an eigenvalue problem. Yeah. So this equation we use to calculate both eigenvalue, eigenvector, that pair. Yeah. So it's the eigenvalue problem. Yeah. All right. So the first thing we calculate, we solve this eigenvalue problem. Linear algebra. All right. Yeah. Key assumption. Yeah, so then, because the whole eigenvalue problem in linear algebra, the theory is relatively complicated. Yeah. And in this class, we will not go that far. Okay, we will not use the whole eigenvalue problem, whole theory about this problem. Yeah, too complicated. So we use the relatively easy part, okay? So that's why we make assumption to make the problem easier, okay? But this assumption, so reasonable, and most of our real world questions satisfy this assumption. Yeah. Okay. So, you know, not 100%. Yeah. But pretty much 90-something%. Right. Yeah. So 90-something%, our assumption, you know, work in the real world application problems. All right. Let's look at the assumption. Key assumption. All right. Yeah. All right. This assumption, this A matrix, we assume it has linearly independent eigenvectors. That's the assumption. Yeah. Because, this assumption, for most of the A, it satisfies this condition. But there is some special cases. Their eigenvectors may not be linearly independent. So there are those cases. That's the harder part of this theory. The harder part, you know, people need to discover the structure. For what structure of A, their eigenvectors are not linearly independent. So finally, so people discover, oh, for this kind of matrix, you know, so their, you know, structure should follow, you know, certain conditions. So that part is very complicated. So we try to avoid that. Okay, we try to avoid that. So if we make this assumption, then we do not need to deal with that part, right? We do not need to deal with that part. Okay, so that's the reason. Okay, all right. All right. So the simpler case. Most applications have this property. All right. So it's pretty good. All right. Then we want also, even under this assumption, this assumption actually covers, you know, let's say 90% of the matrices. All right. Then under this assumption, then we like to look at a few more special cases. You know, those cases that within this, you know, big umbrella, under this big umbrella, but there are a few relatively simple special cases. You know, we can see this property easily. The first special case, when A has n different eigenvalues. This is the first simpler case. A, when you have a matrix, you can calculate its eigenvalues, right? Our condition is where these n eigenvalues, because, so here, this question related to one of our homework concept questions. All right. So, because A is an n by n matrix. Here, let me give you some basic things. A matrix, n by n matrix. Okay. To calculate eigenvalue, do you remember the equation we used to calculate eigenvalue? A minus lambda times identity matrix, its determinant equals 0, right? The determinant, what is its determinant? We know for n by n matrix, the determinant, there is a formula, right? The formula is pretty big, so I do not want to show you here. Okay, 2 by 2 matrix, you know, I can show you. 2 by 2 everybody knows. I do not need to give it to you. For n by n matrix, actually there is a recursion way we can write. Recursion way, okay, but very complicated. So that's why, most of the time people don't want to write it explicitly. But all right. So here I want to say, after you apply that complex formula to calculate determinant, what will you get? you will get a polynomial, right? You will get a polynomial of degree n. Degree n. Polynomial of degree n. You get a polynomial of degree n. Okay? All right. How many roots do you have? Well, you have a polynomial of degree n. Leading coefficient is 1, yeah, because here, lambda times identity matrix. Identity, we know all ones, right? Yeah. Then, the leading coefficient is lambda to the nth. 1 times this. 1 times. Then plus all the other terms. Leading coefficient is 1. How many roots can you find in this polynomial? The general case. I mentioned an important theorem. It's called a fundamental theorem of algebra. Yeah. Yeah, long time ago, I gave you that theorem. Gauss. Yeah, Gauss proved that. Yeah, because that theorem, in math history, well-known theorem. But at the beginning, it was very hard to prove. So, the genius mathematician Gauss, right? Yeah, Gauss gave a proof. Fundamental theorem of algebra. It says this polynomial always has n roots, n, the same number, degree number, n roots. Okay, n roots. Yeah. All right, here. Now we know this A matrix has n eigenvalues, right? Because the roots corresponding to eigenvalues, right? Yeah. So A matrix always has n eigenvalues, but the situation could be complicated because when n has n eigenvalues, some of the eigenvalues could be the same, right? Yeah. Because one eigenvalue, for example, lambda 1, if we do the factorization, lambda minus lambda 1, it could be repeated m times, right? Yeah. So we call it multiplicity is m. Yeah. So then lambda 2 could be repeated, L times, right? And so on. Okay? Yeah. Because each root could be repeated multiple times. Okay? Yeah. Yeah. For the general case. Yeah. But here, this case, n different eigenvalues. N different eigenvalues. That means the determinant of A minus equals lambda minus the first eigenvalue, lambda minus second eigenvalue, and so on. Lambda minus the last eigenvalue, and these n eigenvalues, 1, all these n eigenvalues are distinct. Now, that's a special case, right? Yeah, that's a special case. Yeah. But the percentage is pretty high, right? Yeah. Yeah. For a general polynomial, degree n polynomial, they have distinct roots. The percentage very high, right, in a real world situation. Okay? But when this happens, when your matrix has this property, then our assumption is satisfied automatically. Okay? Yeah. So we can prove it easily. Yeah, the proof is very simple. Yeah. Here I do not prove it. Okay? Yeah. So this case number 1. Under this condition, the assumption is satisfied easily. Okay? Yeah? case 1. For the case 1, you don't worry about the assumption. Yeah. When you have the case 1, you can assume n eigenvectors independent automatically. Because when n eigenvectors independent, then you can write a general solution using n eigenvectors, right? Otherwise, you cannot write the general solutions. That's the problem. That's the problem. Okay? Because our goal, we want to write a general solution for this linear system. If the n eigenvectors, if they are not linearly independent, we cannot write the general solutions out. We have trouble. Okay? Yeah. Case number 2. When A is a symmetric matrix. Yeah. Do you know what's the symmetric matrix? Symmetry. Symmetric matrix in linear algebra. You know transpose, right? You know matrix transpose? Yeah. Yeah. So here, yeah, let me review that matrix transpose concept. Transpose concept. So this is an important basic concept. Transpose. Okay? Yeah. So here probably I give you here. Yeah. Yeah. The entry with respect to the diagonal, if I draw, you know, square, this is a diagonal, right? With respect to diagonal, two locations symmetric about the diagonal, then they have the same value. Okay? If the entry location symmetric, you know, mirror flip. Okay, all right? Yeah. So that's the Aij equals Aji. Okay? Yeah. Jk. A sub Jk, that means the jth row kth column, that entry. Okay? Jth row kth column, that entry has the same value with another entry with kth row jth column. Yeah. These two symmetric about the diagonal. Okay? So if a matrix has this property, you know, yeah, everywhere, okay, yeah, everywhere has this property, then we say it's a symmetric matrix. Yeah. And we define the transpose. Transpose, you know, we flip, okay, yeah, transpose, you know. You know, yeah. All right. Basically, we make rows become columns, columns becomes rows. That's the transpose. Okay? Yeah. Yeah. The way you write the rows, now you write it again, but you write as a column. How about that? That's the transpose. The way you write column, you write it again, but you write it in the row way. That's the transpose. Okay? All right. So, and some people use the, superscript, use a capital T. Capital T, yeah. Most people use capital T, yeah, but small number of people use the lowercase t, yeah. But yeah, more frequently, capital T will represent transpose. Capital T transpose. Okay, all right. Then, for the symmetric matrix, we can write A transpose equals A. That's for the symmetric case. Yeah. A is symmetric, its transpose equals itself. Yeah. If a matrix has this property, then this key assumption, this assumption is automatically satisfied. Okay? Yeah, we can prove it. Okay? Yeah, we can prove it. Yeah. Yeah. Because if a matrix is a symmetric, then the first condition may not, and A has n different values. It's not necessary. That condition is not needed. So a symmetric matrix, even if a symmetric matrix does not have n different eigenvalues, yeah, the symmetric matrix, they could have, some of the eigenvalues could have certain multiplicity, okay? Certain higher than one multiplicity. Still, yeah, the key assumption is satisfied. Symmetric means whatever it's their eigenvalues are, any form eigenvalue. This property we can prove. It has that property. Yeah. The proof also pretty easy. Yeah. All these proofs very easy. Yeah. All right. Number 3, skew symmetric. Yeah. Slightly different. Skew. What's that skew? Negative. Negative. Yeah. So this same but negative. Okay? Yeah. A sub jk equals negative A sub kj. Yeah. Then all the diagonal entries must be 0. Okay? All the diagonal entries, because the diagonal entries, these entries equals negative itself, right? Yeah, because diagonal entries, they are symmetric with themselves, right? Yeah, on the symmetric axis. So those entries, they are symmetric with themselves. Yeah. This condition, those diagonal entries, they are equal the negative copy of their values. Then must be 0, right? Yeah. One value equals its negative 1. This value must be 0. So for skew symmetric, all the diagonal entries must be 0. Okay? Non-diagonal entries, so this property. Okay? For this type of special matrices, our key assumption is satisfied automatically. Okay? No matter your, the form of your eigenvalues. Yeah. Multiplicity, it doesn't matter. Okay? Yeah. Any forms of eigenvalues. Yeah. So these 3 cases, so we have the key assumptions automatically. Okay? Yeah. All right. But other than these 3 cases, so there are still a lot more. Okay? Yeah, but it's hard to describe. Yeah. These 3 very easy to describe. Yeah. All right. So here, give you the background. Okay. So when you work, so you can see, from the big picture. Yeah. So what are you doing? Yeah. All right. Yeah. So with this, let us. Yeah. All right. So there. Because after that, you can find eigenvectors. Yeah. So you find eigenvectors. And after you find eigenvectors, their eigenvectors are linearly independent automatically. Yeah. So you don't worry. And you can use eigenvectors. Because you have n linearly independent eigenvectors, you can use those eigenvectors. You can write a general solution, and you get a basis of the linear system. Yeah, because n linearly independent, that's the basis. Okay, basis of this linear system, ODE. Yeah. So then you use basis, you write a general solution. So we complete the solution. Okay. Yeah. All right. Yeah. Yeah. Basis of the solution. Now, let's look at the basis. Yeah. Yeah. Round scale. Yeah. All right. Why? Yeah. Original equation, n by n, coefficient matrix. Yeah. Yeah. So this problem, so we assume linearly independent. All right. Eigenvector is linearly independent. Yeah. All right. The corresponding solution, now we are ready to write the n solutions in the basis. Yeah. Because we need to find n solutions, linearly independent solutions. And we use these n solutions as a basis for all the other solutions. All right, yeah. So the form is like this. Yeah. Yeah. So each eigenvector, because each eigenvalue you can find a corresponding eigenvector. Each eigenvector, yeah. And eigenvector you use to write these solutions. Yeah. Here, just remind you the key assumption. Yeah, we assume they are linearly independent. Okay, so you don't worry about that. Yeah. Yeah. Because in the general, you cannot assume that. The general case, you cannot assume that. Here, because we only work on the A matrices that satisfy this assumption. Yeah. Fundamental matrix. Yeah. So we defined this concept before. Fundamental matrix. Yeah. With these basis n vectors, linearly independent vectors, the basis functions, we put them together. It's a matrix, right? Yeah. N by n matrix. We call it a fundamental matrix. Yeah. So what's the fundamental matrix? Yeah. Y sup 1, the first vector solution, yeah, it's a column vector, right? The first solution, column vector. Second, each solution is a column vector. So we put these n column vectors together, so we get an n by n matrix. That matrix, we know all the columns are linearly independent, right? All the columns are linearly independent. Yeah. So we put these n vectors together, we get this matrix, we call it fundamental matrix for this ODE. Yeah, fundamental for this ODE. Yeah. All right. Yeah. So here, just review the concept. Yeah. Yeah. All right. So matrix of eigenvectors. Yeah. But sometimes we may like to put all the n eigenvectors together. We also get an n by n matrix. Yeah. This matrix we we use this capital X, capital boldface X represent this special matrix. Because Y matrix, X matrix, they are correlated, right? Yeah. They're slightly different, but they're correlated. So we want to use different notations to represent these two matrices. Because Y matrices, yeah, Y correlated, because the Y, each Y vector contains the E function part, right? Yeah, yeah, containing E function part. X, each vector, it does not contain the E function part. That's the main difference. That's the main difference, okay? All right. Yeah. X is invertible. Why X is invertible? Yeah. Can you explain why X is invertible? Yeah. We review linear algebra a little bit. Because all these n vectors are linearly independent, right? You put linearly independent vectors together in a matrix, square matrix, it must be invertible. Yeah? That's the result from basic result from linear algebra. N linearly independent vectors. Put them together, invertible. You get an invertible matrix. And the determinant must be non-zero. If you calculate determinant of X, non-zero. Similarly, also true for Y. Why? Because n Y vectors, they are also linearly independent. Then Y matrix also invertible. And determinant of Y, non-zero. Yeah. We have the same thing for Y. For X, for Y. Okay? Yeah. Yeah. All right, so let's continue. Yeah. Relationship between X and Y. Yeah. Because only different part is the E function. Those E functions, eigenvalue, E functions, yeah. You can treat, so here, we can write, because that's the Y, all right. Yeah. How to see, independent, right. So the relationship is the Y matrix, you can write as X matrix multiply, this is we call a diagonal matrix. This matrix, it's a diagonal matrix. So if you just apply the matrix multiplication, you can see the product of these two matrices the same as that one. by the matrix, the definition of matrix product. Okay, yeah. Row, column, you can see that. Yeah. So all the diagonal entries, so you put those E functions. Yeah. Diagonal entries. Yeah. All right. Yeah. Yeah. So the linearly independent, so you can see, yeah. So Y matrix equals X matrix, capital X matrix times that diagonal matrix. Okay. Capital A and capital X matrix, determinant non-zero, right? Capital H is determinant non-zero. The determinant of this diagonal matrix also non-zero, right? E to the lambda, adding together, the exponent add up. Okay, non-zero, yeah. Non-zero number times non-zero number also non-zero, right? Yeah. So this tells you the determinant. Yeah. So here we use a, capital. This diagonal matrix. So here we use a capital lambda represent. Yeah. All right. So then let's look at the determinant of product. Yeah. But because here we review another basic property of linear algebra. So we use this chance, we review some basic properties, get yourself familiar with the basic properties of linear algebra. So when you do the calculation, okay? Otherwise, you do not feel comfortable, okay? Yeah. And you can see in our third assignment, we have so many linear algebra questions. 5 plus 5, 10 linear algebra questions, okay? In the quiz number 5 questions for power series, 5 questions for linear algebra. But in part B, you have 5 more linear algebra questions. Total, you have 10 linear algebra concept questions. Okay? So this review part covering those 10 concept questions. Okay? Yeah. All right. Determinant of the product of two matrices, A matrix, B matrix. Here, A matrix, B, they must be square matrices. If not square matrix, it's false. Okay? Yeah. Yeah. But we only look at the square matrices in this class. Yeah. Yeah. But you need to, in the general case, you may have, you may have problem. Okay? All right. So equals determinant of A times determinant of B. A property. Okay? All right. So with that, you can see, the Wronskian. Yeah. So we can calculate the Wronskian. Okay. All right. Yeah. The Wronskian W you calculate of Y equals determinant of Y. Yeah. Wronskian. Determinant of Y. Right? Yeah. Yeah. Here. Determinant of Y. Yeah. All right. So here. Let's do this way. Yeah, the Wronskian here. Yeah. Remember, our previous Wronskian definition is not for linear system, right? Our previous definition is for the nth order ODE. Yeah. So we use that, derivative, so that way, okay? Yeah, that's for that problem. But when we move to this linear system ODE, then we need to change our definition, or we need to do adaptation, the Wronskian definition, and this is the Wronskian definition. But these two definitions, they are compatible. Remember, nth order ODE, how do we convert nth order ODE to a linear system? Remember? Yeah, we use derivative, second derivative, we add new y functions, first derivative, second derivative. Yeah. Here, if you do the same way, then the Wronskian of the old version and the Wronskian of the new version, they are compatible. No contradiction. Okay? Yeah. So here, you can treat, this is our definition of the Wronskian for the linear system. Determinant of capital Y. Yeah. All right. Then, by this basic formula, equals determinant of capital X times lambda, capital lambda, and you can split. Okay? After you split, we know, yeah, so the determinant of diagonal matrix you can write as another E function. Okay? E function can never be 0, right? Yeah, E function, we know, can never be 0. Yeah. All right. Yeah. So the determinant equals this expression, and determinant of X non-zero, yeah, because linearly independent vectors. Yeah. All right. So we know its Wronskian is never be 0. Yeah. Wronskian never be 0, they're linearly independent, right? Yeah. So although we know linearly independent. Okay. Yeah. All right. So the general solution, after we know these n solutions, they are linearly independent, we can write the general solution. How to write general solution? We know general solution is the linear combination of these n linearly independent solutions. Linear combination. So how do we write a linear combination? Here we use the matrix multiplication to write the linear combination. The general solution, yeah. So we know this is a linear combination, right? Yeah. So for each solution, vector solution, we use a constant, C1, C2, a constant. Then we add them together. Yeah. This is linear combination. But this form, can you write it as a matrix multiplication format? Yeah, we can write. Matrix multiplication format is capital Y times a C constant vector. Constant vector C1, C2. That constant vector. Yeah, yeah. The C vector, C1, C2. Here I use transpose, yeah, because the C vector should be a column vector. Yeah. But because here, if I write column vector, I use a lot of space. So I write a row vector to use less space, but I put a transpose on it. I make it a column vector. Yeah. All right. Yeah. Yeah. Now, that's the preparation. Okay? So here you can see I spend a lot of time. So review linear algebra, basic knowledge, and also get yourselves familiar with the environment. So when we solve the linear system, so you know what you are doing, right? Yeah, you know what you are doing. Yeah, yeah. The understanding, basic understanding. Yeah. All right. So we're near the break time. Yeah. So when you come back, so let's do the example. Yeah. C.2. Yeah. Method of undetermined coefficients. Coefficients undetermined. We need to determine the coefficients. Yeah. Actually, we generalized the old method from, yeah, in our module 2. We learned the undetermined method, right? Yeah. Yeah. So here we generalize. Yeah. All right, but we need to work in the matrix environment. Yeah. All right. Yeah. After 10 minutes, we continue our second part. Yeah.